Tobias Polin. I currently do a PhD at the Norwegian University in Science and Technology in Trondheim, Norway. So the work I am presenting today is part of collaboration with Nexans Norway and SINTEF, which is a research institute in our city. So we'll go through the motivation for this kind of study, tensile testing, microstructural investigation, an example of creep models, then how this could be calibrated for being used in a component full-scale model, then the fundamental creep mechanisms active, and the kind of step test that we perform to try and understand at which load these mechanisms are active. And then some preliminary fatigue results that we obtained and so conclude. So in subsea power cables, to prevent the cable from failing from short circuit, electrical short circuit, we need a watertight barrier. And what is used is a very, very ductile metal layer, because it's stable and it's watertight. And that is, in this case, lead alloys. This is not a new technology, it's quite old indeed, but most of the works have been done several decades ago, and now there is a new interest from this industry to try and understand if it's possible to vary the amount of material due to economical and environmental concerns mainly. So we performed some initial tensile testing, and that is made basically by unfolding, cutting open the cables and unfolding the sheeting and producing dog-bone specimens from it. We had to use digital image correlation because it's extremely ductile and it's impossible to trust the displacement of the clamps. Performing this testing from 10 to the -7 seconds to the -1 strain rate to 10 to the -3, we have a clear influence of the strain rate on the stress reached, and that is caused by the creep that is active. Even at these are room temperature tests, but these alloys melt around 300–320 degrees Celsius. So even at room temperature, we are at recrystallization temperature, basically. There is also an influence of the thickness, and because we did this testing for different extruding thicknesses from 1.1 to 1.8 to 3.3 millimeters of thickness of the sheeting layer, and the thicker specimen has always a higher stress level reached for a given strain rate. There's 10 to the -3, -5, -7. The idea is that this is influenced by the microstructure, and indeed the thicker specimens at 3.3 are found to have an average grain diameter which is bigger than what is found in the 1.1 and the 1.8 millimeters of extrusion. So this would basically make the creep deformation harder. As an example, what we want to do is to calibrate the material models and then to use them to reproduce the full-scale component behavior. These are two quite known creep models that are already available in commercial softwares. And in the case of the Anand creep model, that is fairly complicated. There's a quite big number of parameters that have to be calibrated, but will give good results in this area, this plateau. This is for a constant strain rate, a constant stress reach, that is a secondary creep region, while the strain hardening power law creep, although it's it's much simpler, it has only 3 parameters to calibrate, it's not able to reproduce this part of the behavior. an example of the calibration that can be done is using Abacus and eyesight modeling the specimens, the test in Abacus, and then matching the data extracted from the finite element simulation with the experimental data, and then running an optimization loop that will find the array of constants starting from intervals that have to be set by the operator according to, they have to be intervals that make a physical sense, so for example, for the activation energy. Creep mechanism might be due to diffusional flows of vacancies and sliding of the grain boundary, or dislocational flow, or we can also have creep nucleation of fractures and propagation, time-dependent crack propagation. So to see at which kind of load each of these mechanisms is active, we tried to run a traction test with multiple loads. So basically bringing the material up to 8.5 MPa and then holding for a certain time in order to reach a steady state creep condition, and then lowering the load and holding, lowering the load and holding. This was done starting from a higher load and then lowering, because it provides much shorter delay, much shorter time in the primary creep, because what we wanted to obtain is the steady state exponents. And what we can find is that the steady state stress and the steady state strain rate are correlated, and obtaining a value of the stress dependence exponent that indicates a diffusional flow up to 5 MPa and then dislocational creep flow from 5 MPa and beyond. We could not calibrate yet the dependence in this case from the average grain size, because we didn't do enough tests with several grain sizes. But this was performed on 3.3 extrusion thickness samples, 3.3 millimeters. Also, we have run different kind of fatigue tests, that is on plain specimens, so without stress intensification, and notch specimens. Here there is a small notch that has been practiced to simulate the presence of defect introduced or hard particle introduced during the production of the cable, and then full-scale bending tests. What we have found is that there is clearly a dependence on the strain rate of the strain rate on the fatigue life of the material. And so in this case, this curve is made at 10 to the minus 2 and 10 to the minus 3 seconds to the minus 1 strain rate. And we have a change of slope and resistance performed on the same alloy, 1.8 millimeters of extrusion thickness. While in the case of notch specimens, this was indeed a different alloy, but still quite similar in the behavior. And we have tested notched and unnotched specimens at 2 different frequencies. And although it might appear that there is a difference between the notched and the unnotched samples, this is the nominal strain range that was set during the testing. And because looking at the failures in this case, most of the failures in the notch samples did not originate from the notch. So I suspect that there was indeed something going on with the testing, and this was maybe put at a real higher strain range, because we did not see that, looking at the fracture, that was not this negative effect of this small notch. So that was probably too small to compete with the with what is already the fragility of the grain boundaries of these alloys, and there is where we observe the cracking. So the idea would be to be able to predict the fatigue life of these alloys in operation, and that might be done by correlating creep properties with the fatigue properties, and this is an example of relatively assessed methods such as damage summation, and we can add the damage caused by the creep as ductility exhaustion or time exhaustion, or a frequency modified strain life equation. But the practical difficulty is the validation of this, because these cables are deformed by thermal loads and sea movements, such as tides. So what is experienced by them in practice is a far lower strain rate than this, and doing this practically in laboratory would require a very, very long time that is unfeasible. Nor we would like to just trust an extrapolation by just these curves at the lower strain rates. So yeah, to conclude, we observed that for this material we have creep deformation at room temperature, that the stress level is influenced by microstructure, and we can have an insight on the deformation active by looking at the correlation between the stress applied and the strain rate that we obtain. And these effects have an influence on the fatigue life at different strain rates. So in the future we would need further investigations for different grain size, and in situ testing would be also useful to try and understand better which are the mechanisms active on the material in order to have in the future a more conscious design. So thank you for your attention, and if there is any of you who has experience with similar topics, I would greatly appreciate the talk.